This is the pre-lab video for the heat of dissolving lab. Now experimentally this lab is very straightforward and pretty easy. So at the top of this page where it says purpose, the purpose is to measure the temperature as different solids dissolve in water and determine the molar heat. Now the very bottom of here is where the data table is, and what you're going to do procedure-wise is you're going to measure out between 8 and 10 grams of these two solids here, ammonium chloride and calcium chloride. And you're going to use a graduated cylinder to measure out exactly 100.0 milliliters of water. You are going to, one at a time, dissolve the solids into the water and measure whether the temperature goes up or down. And you're going to record either the highest or lowest temperature that is reached. You're going to classify them as exo or endothermic, and then you're going to go through the calculations to figure out the delta H for the reaction. So what I'm going to do in this video is I'm going to actually make up numbers for a solid that you are not going to do. So I'm going to write this down on this page here. What I'm going to go through is using the solute of potassium fluoride. So we'll write it as KF. Now I'm just going to make up some data here so you don't have to copy this on your lab, but I'm going to say I'm using 9.00 grams of the solute. When you are doing the lab, don't feel like you have to get it exactly 9.00. It's just anywhere between 8 and 10 grams. It doesn't matter what you get, just make sure you write down the exact number of what you use. Now since it says 100.0 milliliters of distilled water, water has a density of 1.00 grams per milliliter, so that is the same as saying 100.0 grams. The mass of the solution, and this is a part when people are doing the math that they forget about, the mass of the solution is you're just adding up the solute and the solvent, which in this case is the H2O. So remember, when you add, you go by the least number of decimal places, which 100.0 is one decimal place, 9.00 has two, so you get 109.0 grams. The initial temperature, now in this made up data, again, I'm just going to make this up. The initial temperatures, I'm using 21.3 degrees Celsius. And for the final temperature, I'm going to say 26.8. It would be somewhere around there for this experiment. All right, so whenever you do delta anything, it's always final minus initial. So you're doing 26.8 minus 21.3. Again, go by the least number of decimal places since you're subtracting in this case. And it's 5.5 degrees Celsius. They're both one decimal point, so that's what I'm going to do. And since the temperature went up, that ends up being exothermic. So this is the data that I'm going to use for the rest of this video. Now there's two pages that look exactly the same, and it's because you're going to do the calculations for the two solids that you do in the lab. So for me, I'm working with potassium fluoride, so that's what I'm going to write up here. Now it says calculate the change in temperature. Remember, whenever you're doing this stuff, you always have to show all of the work. So it's 26.8 degrees Celsius, subtract out the initial temperature, which is 21.3 degrees Celsius. That gives you that change of 5.5 degrees Celsius. And pay attention to significant digits and all that. Like I said on the first page, since these are both one decimal point, when you subtract, you go by the least number of decimal points. Now here it says Q surroundings. It says calculate the heat absorbed or released by the solution. Now since our solution went up in temperature, it went up by 5.5 degrees Celsius, what happens is the solution absorbed all of that heat that the chemicals released. Remember, there's 2 points of view when you're looking at this. You have the point of the view of the chemicals and you have the point of the view of the surroundings or the solution. If the chemicals, well, I should say if the solution went up in temperature, it means it absorbed heat. So the chemicals had to release that heat. So whatever the chemicals do, the surroundings do the opposite. So this says Q surroundings, and the other way people write it sometimes is the heat of the solution, which I'll just abbreviate SOL''N. It doesn't really matter if you say surroundings or solution. The mass of the solution, and this is the part that people will make a mistake on sometimes, and it throws everything off. The solution is the solute plus the solvent. The solute for us was at 9.00 grams of potassium fluoride. The solvent was the 100.0 grams of H2O. So we have to add those together. So make sure you use that 109.0 at this point, or whatever mass it's going to be for you, because it probably won't be exactly 109.0. But make sure you use the mass of the solution, not the solute or the solvent, but both of those combined. Now we have delta T is 5.5 degrees Celsius. And then we have the specific heat of the water is 4.184 joules per gram degree C. The grams will cancel out. The degrees C will cancel out. What you'll be left with is joules. On the calculator, you get something like 2,508.3, and there are a bunch of numbers after that. And now that's joules. Now there's two things we want to do here. If you look at the very bottom of the page, where it also says in the number 6, we are solving for kilojoules. So I want to take this number and convert it to kilojoules, and at the same time, I want to match up the number of significant digits. So what we have is 5.5 degrees Celsius. Looks like I put an extra line there. That's 2 significant digits. 109.0 is 4, and we never go by the specific heat of water because that is a constant. So that's going to give us 2 significant digits. So I'm going to write it as 2.5 kilojoules. So I got the significant digits, and I divided by 1,000 to get the kilojoules. So this is how much heat the surroundings or the solution, the water, absorbed. So that means the reaction had to give off that same amount of heat, but we changed the sign. So if the surroundings went up by 2.5 kilojoules, the chemicals went down by 2.5 kilojoules. So it says, use the periodic table, calculate the molar mass of the solute. So potassium off the periodic table is 39.1 grams per mole. Fluoride is 19.0. We just add those up, and you get 58.1 grams per mole. And then we're going to have to convert or calculate the number of moles of solute that were used. So pay attention to the wording. Right at this point, it is asking for the moles of solute. All right, I'm not talking about the solution. It's just the solid that was dissolved. So I started off with 9.00 grams of potassium fluoride multiplied by 1 mole of potassium fluoride over the molar mass, which is 58.1 grams. Potassium fluoride, remember whatever units I start off with, they should be on the bottom in the next step, so they will cancel out. Rounding off the 3 significant digits will give me 0.155 moles of KF. Make sure you label all of this stuff, because if you don't, it'll be very easy to make a mistake. Now, if we're talking about molar heat of solution, it is the heat of the reaction, which was measured in kilojoules, and it's going to be divided by the moles of solute that were dissolved. So for delta H, the heat of the reaction for us was at negative 2.5 kilojoules, which should make sense. We said delta H is always from the point of the view of the chemicals. So the chemicals have a negative delta H. They release that heat, and that is why we saw the surroundings go up in temperature, and that's what we say happens with an exothermic reaction. So the moles of solute used were 0.155 moles. So when you do this division, you get negative 16.1 kilojoules per mole. And what I end up doing is, since this is 2 significant digits, I'm actually going to round that off to 2 significant digits, so I get negative 16 kilojoules per mole. Now the percent error. What I don't have it written down here at the bottom, but for the solids you're going to use, I give you the accepted delta H's. For potassium fluoride, the accepted delta H is negative 17.7. And what we're doing is subtracting out this experimental value, which is negative 16. And we're going to divide by the accepted value again, which is 17.7. There's going to be absolute value bars. You're going to multiply by 100. Make sure you do the subtraction first. So when you do this, it's negative 17.7 and then it says minus a negative 16, which is basically like saying plus 16. That gives you a negative 1.7 difference. It's going to be divided by negative 17.7, and this thing's blacking out again. All right, and then you multiply that answer by 100. Now, since there was two significant digits, you're going to round that off to two significant digits, so it looks like it's going to be something around 9.6% error, which makes sense. It was supposed to be 17.7. We got it around negative 16, so it's not right on. Now, at that point, that's how you do the calculations for these. I think the most common mistake that I have seen is not doing the mass of the solution. It's very easy to make a mistake on that if you're going too fast. Now for the back page, there's one other thing I wanted to show you on the back page, and it is writing the reactions for this. Overall, writing a reaction for something that dissolves, an ionic solid that dissolves, it should be pretty straightforward. All it's doing is dissociating, so it's breaking apart into its ions. Now to give you an example here, sodium chloride. I'll do the same thing with potassium fluoride. So you have potassium fluoride that started off as a solid. You put it in water and it dissolves, so those positive and negative ions are going to dissociate. So you end up with the potassium cation, and it's in solution, so I'm going to put AQ for aqueous. You have the fluoride ion, which is -1, and again, that is aqueous, that is the anion. Now, the one thing that throws people off sometimes with this is, let's just say you're working with something and it's K2Y, and Y is just this made-up anion, right? You would have a solid there, so pay attention to what's going on. You would have potassium, we know that is +1. Now, this Y is a made-up thing, and since there's a 2 here, we know that it would have to have a -2 charge, and it would still be aqueous, but you want to balance these things. So if there's a 2 over here for potassium, you would put a 2 there for potassium, and it would end up balancing. It would say you get 2 potassium ions and 1, whatever this Y is, this 1 ion. And that is how you do that. So the part that takes a long time with this lab is not the procedure, but the calculations.